Today we're going to be talking about exponential models and functions, and then focus more on exponential growth. So an exponential function is a function that has your variable x in the exponent. And the mother function is y equals a times b to the x, where this a value right here is your starting amount or your y-intercept. When x equals 0, that gets your y-intercept. And b is your growth rate or decay factor. It might be similar to the slope, but for slope we were adding a number each time or subtracting a number each time. For a b value, we are multiplying each time, and that number we multiply by could be a fraction. So exponential growth, y equals a times b to the x, where a is greater than 0, so a is positive, and b is greater than 1. In the exponential decay, it looks the same, and a is still greater than 0, but b is less than 1. And b always has to be a positive number. We can't have a negative b value. That wouldn't be an exponential growth function or exponential decay function either. And then the a values have to be bigger than 0 for us to have growth or decay. We can have an exponential function, negative 3 times 2 to the x. That is an exponential function, but that's not growth or decay. It's neither of those. So let's look at this table and see, can we figure out, are these exponential growth or decay functions? Find the equation and explain why. So if we look at the y values here, see what's happening each time. We're multiplying by 6. So since we're multiplying by a big number bigger than 1, this is going to be exponential growth. And our b value is 6. And our a value is our y-intercept, which is 2. That makes my equation y equals 2 times 6 to the x. And it's a good idea to put the parentheses around the 6, so you know that's the only thing being raised to the x power, because in an exponential function, that b value is the only thing that you are raising to the x power. And the reason why it's growth is that because b is bigger than 1. B is bigger than 1. Now if we look at this one, you see, well, we're dividing by 3 all the way down. 27 divided by 3 is 9, 9 divided by 3 is 3, but in exponential functions, we are always going to multiply. So instead of saying divide by 3, we're multiplying by 1/3 each time, times 1/3. So our b value is 1/3, and our a value is 27. That makes my equation y equals 27 times 1/3 to the x power. And that's going to be decay, because b is less than 1. Now in this problem, you'll notice that our y values are being multiplied by 5 each time. So b is equal to 5. But my a value, we don't see that right now. So we have to extend this table and say, okay, when x is 1, if we're going backwards, we're going to divide by 5. And you can double check and say 1 times 5 is 5, 5 times 5 is 25. So this means my a value is 1. Equals 1 times 5 to the x. You don't have to write the 1 there, because if you don't, it's just assumed to be an invisible 1. Growth or decay, this is growth, because a is bigger than 1. Now down here, we're going to create a table And in the table, we're going to start at 0, 1, 2, 3, 4. And we know that this is our y-intercept. And then this is our growth rate, so we're going to multiply 2 each time. 8 times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128. And this is growth because our b value is greater than 1. Our b value is 2. Here, you could say that you know that this is going to be decay because our b value is less than 1. Your b value is 1/2. 0, 1, 2, 3, 4. And we start at 20, and then we go down by half each time. So 10, half of 10 is 5. Half of 5, we always want to keep it as fractions as long as possible. So 5 divided by 2 is just 5 divided by 2. And then 5 over 2 divided by 2, again, can be written as times 1/2, would be 5 over 4. And that would be our table here. On the next page, we're going to talk about the graph of exponential growth functions. That term asymptote comes back from when we were graphing the rational functions. Remember, an asymptote is a line that a graph approaches more and more closely, but we never cross it. So here it says the function y equals b to the x, where b is greater than 1, is the parent function for the family of the exponential growth functions like we talked about before, with a base 1, because there's no number out in front, there's no a value. The general shape is done below. And you can see 0, 1 is a point on the graph, and 1, b is another point on the graph. The domain of exponential functions is going to be -infinity, infinity. The range. If you look at this graph here, if we look at the left, our y value gets smaller and smaller and smaller, but it never touches the x-axis or y equals 0. So that means our range is 0, infinity. When we were doing rational functions, our asymptotes were x equals a number, but when we're talking about exponential functions, it's y equals a number. And it's always going to match up with the range. Our graph approaches 0, and it gets infinitely close to 0, but never reaches there, so that is your asymptote. And as I've said before, the a, h, and k for our transformations is going to come back, and down here you can see it has come back. A always tells us the shrink or stretch. And if we have a reflection or not. And as we talked about at the first page, if you have a number out in front, that is your y-intercept instead of 0, 1. Up here, there is no a value, so it was that invisible 1. We translate the graph horizontally h units, and remember it's the opposite of what you would see. And then we translate the graph up vertically k units, and it's exactly what you see. So we're going to graph these somewhat similar to the radical functions where we made the table and then that third row. But our y values are going to be a little bit different. You know, in the cube root graph or table, for example, we always started with the same x and y coordinates, and then we multiplied by a. Here, we're going to start with the same x coordinates always, but the y's will depend on our b value or our growth rate. Now, when we graph these, we're only going to do 2 points. Up here, we had 0, 1 and 1, b. We are going to make a table, and the table is not going to have a lot of points, but we just need to know the general shape that this goes in. So first, let's identify our values. A is 1/4. B is 6. We don't have an h or k value, so those are both 0. Our asymptote is always going to be y equals 0 unless we have a vertical shift up or down, and then that will change our asymptote. So that'll be y equals 0. Domain is always -infinity, infinity. And our range is going to be 0, infinity. Because our a value is positive means our graph is going to go up. And the reason we have a parenthesis around that 0 is because an asymptote is a value we approach but never reach. So 0 is not going to be included. We put a parenthesis around it. Now for our table, we're going to start off with 2 points. We're going to talk 0, 1, and then 1, b, and b is 6 in this case. Then our third row here is going to be 1/4 times y, our a value. 1/4 y. So 1 times 1/4 is 1/4, and 6 times 1/4 is 6/4. And if you want to make that a decimal of 1.5, you could. So then we're going to cross this off. We're going to plot 0, 1/4, and 1, 6/4, or 1.5. And then our graph is going to look like this. And that's all we have to do. Now, if we had to translate it left or right, we would then do that based off of our h and k values. Now, over here, we have some h and k values. So if we look at this, the number that is being multiplied out front is 2, so that is our a value. 3 is being raised to the power, so that is b. Our h value is 2, and our k value is -2. So what that means is that our asymptote is going to be at y equals -2. Our domain, -infinity, infinity. And our range is going to be -2, infinity. Now for our table. We have 0, 1, and then 1, b. Our b value is 3. And then we're going to multiply everything by 2. 1 times 2 is 2. 3 times 2 is 6. So that means now I'm going to graph 0, 2, and 1, 6. And my graph originally will look like this. But I need to move my points, right 2 and down 2. So 1, 2, and down 2. Right 2 and down 2. My asymptote is going to be at y equals -2, so we should draw that in because it's not on the x-axis. It might be harder to visualize. Then my graph will come through and look like that. If we look at the next page here, it says -2 to the x power. That negative is not tied with the 2 because you would see parentheses around it. What this means is that our a value is -1, our b value is 2, our h is 0, and our k is 0. Our asymptote is still going to be y equals 0. Our domain is -infinity, infinity. Our range, though, because a is negative, it's actually going to be 0, -infinity, 0. And that will make more, if that doesn't make sense right now, it will once we see the graph. So here's our table, x, y, 0, 1, and 1, b, 2 in our case. And then that third row where we multiply everything by -1. So now look what happens to our graph. We have 0, -1, and 1, -2. So our graph actually goes like this. Right, now down here, we're going to talk about an exponential growth model. So when a real life quantity increases by a fixed percent each year or other time period, the amount that we use, or the equation that we use to figure out what it will be worth after a certain amount of time is this equation. A times 1 plus r in parentheses raised to the t power, where a is our initial amount, r is our percent increase as a decimal, and when 1 plus r is our growth factor, or our b value. So this could be linked to where this b value is our growth factor. Okay. So let's look at this word problem down here. It says, in the last 12 years, an initial population of 38 buffalo in a state park grew by about 7% each year. So 38 buffalo, that's our initial amount. The r value is our growth rate, but 7% as a decimal is 0.07. Don't make the mistake and say, oh, it's going to be 0.7. 7% is 0.07. So y equals 38, our a value, times 1 plus 0.07 raised to the t power. Now we can simplify that inside the parentheses as to y equals 38 times 1.07 times raised to the t power. So that is our equation. We already did letter B, says identify initial amount. We did the growth factor, and it should say percent increase. This is about how many buffalo are left in the park after 7 years. Well, we're going to plug in 7 for t. Oops, I forgot the 38. So in our calculators, 38 times 1.07, oops, close parentheses, raised to the 7th power. And that's 61.01. So really close to about 61 buffalo. You graph the model and use a graph to estimate the year where there were about 53 buffalo. So we know one point is 0, 38, because that's our initial value. And we know that we have 61 buffalo after 7 years. So our graph would look like this. And the question is saying, what year will we have 53 buffalo? So we're estimating. So everyone's answer might be a little bit different. So 53 is close to 50, and that's between 40 and 60. So I'm just going to go here and say, that looks like between 5 and 6 years. So we can say between 5 and 6 years. The last thing we're going to be doing is talking about compounding interest. And that's another type of exponential growth that banks use to calculate how much money you would have in your savings account after a given amount of time. We have some different terminology, though, when we're talking about this. The first term is called the principal, and that's your initial investment or your initial value or your y-intercept. So the principal is your initial investment. And then the equation you're going to use is this. And it looks a little bit similar to the model that we just talked about. But you'll notice that there's that divided by n and then that n times t power instead of just t. So we're going to be plugging stuff into this formula. The only difference between this formula and the last formula is that n value. And that n value is how often your investment or your money is compounded each year. And this is where we look to see what our n value is. We match up the words. So if it says semi-annually, your n is 2. If it says compounded monthly, it's 12. And that should make sense because there are 12 months in a year. Semi-annually, half a year. There are 2 halves of 1 year. So let's look at this example down here. It says you deposit $2,900 in an account that pays 3.5% annual interest. Find the balance after 1 year if the interest is compounded monthly and annually. So the principle is going to be the same for both of these problems. Your interest rate, again, we want this as a decimal, so it's 0.035. Our n, when we say monthly, our n is 12. When we say compounded annually, our n is 1. And that comes again from this stuff up here. T, it says 1 year. And A, we need to calculate. So A is equal to 2,900 times 1 plus 0.035 divided by n, which is 12, raised to the 12 times 1 power, because the formula says nt, n times t. Oops, I'm sorry, down here t should have been 1. Letter B, A equals 2,900 times 1 plus 0.035 over n, but in this problem n is 1 because it says annually, raised to the n times t power, so 1 times 1 power. So then we're just going to type it into our calculator. If we use parentheses, we can type it in exactly as I wrote it. So 2,900 is 1 plus 0.035 divided by 12, close the parentheses, raised to the 12 times 1 power. And we get $3,003.14. Now you might say, well, why do we have to multiply 2 times 1 in the exponent? Isn't that, or 12 times 1 in the exponent? Isn't that just 12? Yes, you could do that. Again, I just like to type everything out as written. Like I'm even going to type out the 1 times 1 over here. So on this side, 2,900 parentheses 1 plus 0.035 divided by 1, close parentheses, raised to the 1 times 1 power, and I get 3,150. So you see we got a little bit more money by compounding monthly as opposed to annually. So if you really write out your information like we did right here, the PRNT, it becomes so much easier to just plug this into your formula and use your calculator. So make sure to please write these things out. So what I want you to do is to try the solo problem right here. Compounded quarterly means that your n is 4, and 3.72% means 0.0372. So go ahead, pause the video, and try this out and see if we get the same answer. All right, so my answer was $5,587.45. Hopefully you got that same answer. Now, if you rounded it a little bit different, it maybe got 46, 44. That's fine. Just try to make sure you round consistently to 2 decimal places because we are talking about money. Now let's look at number 7. It says how much money must be deposited right now in an account paying 8% annual interest. So that means 0.08 compounded quarterly. Okay, so the n is 4 again. for your balance to have $1,000 after 10 years. So T is 10, but I'm not starting with $1,000. I don't know what I'm starting out with, but I want it to be worth $1,000. So it's going to be 1,000 equals P times 1 plus 0.08 divided by N, which is 4, to the 4 times 10 power. So now we actually have to do some algebra. We can't just plug it in the calculator once and be done with it. We can do 1,000 equals P. We can type this into the calculator, though. One plus 0.08 divided by 4. That's 1.02 to the 40th power. Well, we can do that. We can type 1.02 to the 40th power. Okay, so 1.02 raised to the 40th power gives me 2.21. So 1,000 equals 2.21 times P. Now this is just a simple divide both sides by 2.21. So 1,000 divided by 2.21. And we get $452.49. $452.49. Okay. So we have to put that much money in first, and then in 10 years, I'll have $1,000. Right, so thank you for watching. This has been just an introduction to exponential growth, and you can see that there's a lot to it, but it's just knowing the formulas and being able to plug stuff in and using that calculator. So thanks for watching. Make sure to like this video and subscribe.